Hey folks, welcome back to the series on creating an MLLM from scratch. In the previous video, we saw how MLLMs are typically built, like how does their architecture look like. There is a base language model, and then you have different modalities being piped in through their respective models. Our goal is to just consider one additional modality, which is images. So yeah, we'll basically see where we get. For this video, I would be talking about the language model that we will use as a base. In the next video, we will see the image model, and then we will just try to combine them together and train them jointly. So for the language model, I decided to use Phi3, which is the new small language model created by Microsoft. By small, it is still, I mean, it's still a billion parameter, like multiple billions of parameters large, but it gives pretty good performance. And I think since our goal is to train on a consumer GPU, why not try with a small and good performing model? And the good thing is Microsoft has released instruct versions of the model as well. So that will be super useful. So just as an overview, this paper came out recently, and we will be using Phi3 Mini, which is a 3.8 billion parameter model. And apparently it gives pretty good performance on the standard benchmarks. And they say it is comparable to much, much larger models. The thing what makes Phi3 tick is that it has been trained on really high quality data. So there was this paper, Textbooks Are All You Need, where the authors trained the model on really good quality textbook data. And that's what makes these models tick. Since our goal is just working with the smallest version of 5 models, I'll quickly overview the architecture. But basically, it's a standard decoder architecture, and its position embedding is the rotational one with a context size of 4000. Because Microsoft wanted it to be used on embedded devices and so on, they use the Llama 2 tokenizer, which has extended support across all these embedded devices because of Llama C projects and OLlama and all the other things. So the tokenizer that they use for the Phi3 model is the same as the Llama 2 one. I think for the other models, the small and the large ones, I think the tokenizer is different. Here they use tick token and so on. We already talked about training. You can check out this technical report where they have the results of Phi3 Mini, and it's pretty decent. So, and I don't think I've seen other folks try out Phi3 as a MLLM, so I think it will be a good starting point for us. These models are released on the Hugging Face repositories, and there is a model card for it, so which basically tells you how to run the model, how to train the model, and we will just be going over the code for just training and just running the model. So what else? Let me see. Is there anything important? Yes. So the way they have trained this is they've used fine-tuning. They've used pre-training on a lot of like large high-quality data, and then they have aligned the model using DPO, which is a preference optimization technique. So it is a chat model. So I guess there would be a non-chat variant and a chat variant. The chat variant uses this kind of a template where you can talk to the agent, and you have special tokens for the user and the assistant's response. So it's been trained to do something what ChatGPT does. Let's see, is there anything useful? Yes, so here they say they did DPO, anything. So they trained on 3.3 trillion tokens, which is pretty good. So I guess the Chinchilla papers say that you need to train, if your model is 1 billion parameters, it needs to train on 20 trillion tokens, or times 20, something like that. Oh, sorry, 20 billion tokens to be optimum. So I'm not sure. Like I I have to go back to the scaling papers, but this seems like a decent amount for a small model. All right, yeah. So the codes that I will go through are slight modifications of the code that already lives in this page, and basically I'll just be doing a walkthrough because I think all this is needed when we actually combine the models together and start fine tuning. So let's jump into first just checking out the model and running it. And here, okay. So I have a Jupyter notebook pulled up here. So let's first load in the model. And I will load in the instruct versions, and since I have a GPU, I'll just like put them on my GPU. Let's give it a minute. Since I'm on a Windows machine, I don't have the flash attention built in. I guess for Windows you need to compile it from source or build it from source. I just haven't had time to do it. Okay, as soon as I load the model, I see special tokens have been added to the vocabulary. We'll see what that means in a bit. So first, let's, okay. So for a chat stalled conversation, note that we had to, in the previous page, you saw that there was a user tag and an assistant tag, right? Hugging Face gives you, or this transformer package gives you a nice way of generating that. So the way you generate is you put your messages in this list of dict fashion, where the role would be user or assistant, and then what should the conversation be. Now, if there was a multi-turn conversation, then I would have multiple dictionaries. And then all you have to do is you take your message, and then you just, with the tokenizer, like apply chat template, and then it will put that in that form. So let's see how this looks like. Okay, so basically it has tokenized this chat format, and yeah, so right now it's meaningless because these are just tokens. So let's decode it and see how does it look like. So I will decode it. So start of sentence token, and then this is your user tag, and then the question, and then an end tag, end of question or end of statement. And then again, you begin with the assistant tag. So this is what this apply chat template thing does. Okay, so let's just let the model generate the response. And I just put the input onto the GPU device because everything needs to be on the GPU for things to work. And boom, we have an output. So now let's see what the output is. This was a user question, and then the model generated some answer. It kind of looks sensible. So this is basically like how this will work. And since we only had 32 new tokens, or we set generate only for 32 more tokens, that's why there was the output was truncated. Okay, so remember we talked about this message that came out about special tokens has been added to your vocabulary. So let's see what that is. Okay, so when I check my tokenizer, I see that it has the vocab size is 32,000, but it goes till 32,010. So what that means is 32,000 are the tokens that were used in the pre-training of the model. And then when we did instruct tuning, additional tokens were added. And these are useful for in this instruction chatbot style. So for example, you can see there is a user, there is an assistant, there is end of text, system, end. So these are things that are useful for, so these tokens will be used for in the chat environment. And then you see also placeholder tokens. So if you want to add some new functionality without, rebuilding the tokenizer or adding more items to the tokenizer, there are these placeholder ones which you can use however you seem fit. You'll have to train the model to use those tokens, but then there are some additional placeholders built in. Finally, let's take a look at the model architecture. You can see 32064, 3072. Okay, I don't know why is the difference between that and this. Okay, not so important, but I'm not completely sure why it's 32064, and here we see 32011, because even if I do, it would tell me that it is 32011. I'll have to circle back to this one, but for now, I guess it's not so relevant. Maybe I'm missing something like simple. Okay, so the different layers that are present are your standard 32 layers of attention layers, where you have rotational embedding. That's fine, and also the RMS norm. So pretty standard architecture. All right, so now that we've seen roughly how to use the model, let's see some simple fine-tuning of this model. Okay, so here I have a notebook which is pretty much the code from the Hugging Face repo regarding fine-tuning Phi3. And this uses two libraries, TRL1, which is the Hugging Face friendly reinforcement learning library. It supports PPO, and I believe it supports DPO as well. And actually, I think it does. Let's see. Yeah, of course it does. Like, I think that's it also supports ARPO, and I guess you will be using DPO because it's very efficient and it doesn't need an additional model to train. So sorry, I had a brain fart. Let's go back. So and also we will use some PEF techniques like LoRA for this training. So let's get started. I import all the libraries, and here we define some training config. Right now this is not so relevant because these are all like standard parameters that we have set. And we also define the LoRA configuration. We take the adapter or the rank to be 16 and the alpha parameter, and basically we will apply this LoRA to all our attention blocks, and basically all fully connected layers will get this. So let's set this up, and then we just set up the parameters. So everything is set, and let's see. So what this has done is I have my training config set, and then I have my LoRA config set. So now what we are going to do is we will load the model and basically let it load. And again, I am loading it on my GPU machine. So just let me walk through the code a bit. We just load the model, load the tokenizer, set the maximum length, set the pad tokens, and what side of padding do we want to do. So we'll let the model load, and then here again you see pad token is 32,000, and the what are the other tokens? And I guess somewhere down here you should have the special tokens as well. Yep. Okay, so yes, it's here. Great. Now that we've loaded all our model, we have to define the chat template. So if you remember, like from the previous video, or previous sections, we add this function apply chat template, which would just basically tokenize the conversation in the form that we want. So here we just basically define a function which we will apply on the dataset. And for this one, we just picked up a random Hugging Face dataset that has conversations. Ultra Chat will go through this dataset, but we just pick the dataset, and then we using the map function, we apply the chat template. And this takes in 2 arguments, the tokenizer, so the message and the tokenizer, and then you just pass the tokenizer and then do the same thing for training and test. So let's do that. And okay, let me step back. Here it is doing its thing. Just to hurry things up, I might, when we train or when we apply the tokenizer, I might reduce the size of the data set. And here that is. So here for the train, I just select the first 1,000 items, because again, we're not doing any full scale training here or fine tuning here. So let's just take this. I'll select like only 1,000 items. That's done. And then what we will do is set up the SFT trainer. So, okay, so how is SFT trainer different from your regular Hugging Face trainer? So in your regular Hugging Face trainer, what you do is you train on the next tokens. What the SFT trainer does, it is more like an instruct trainer. So basically, you can specify training only on the generation. So if you have a human question and then a response, you can train the model to only train on the response that is generated. That's why this is useful. So you can only train on the responses or whatever things that you want to train on and leave everything else as is, not do the regular next token prediction. Like the loss is always next token prediction, but then loss should be only computed over certain sections, like where the model generates the values. This is typically used in the chat fashion where people use instruct tuning. Yeah, that is the way this is done is, so when we tokenize, there is a mask parameter that will mask the losses. All in Hugging Face, if you want to ignore losses for a particular token, you put the value -100, and that's what it does. Again, I don't want to go into the too details because that is not the point. We will delve into the details when we actually construct the model, not right now. So this is just to demonstrate, all the tools in our toolkit. Yeah, and then basically we define the model, the training config, the PEFT config, dataset, test dataset, and then we start the job. And it is creating the split, and then soon it will start training the model. So that is pretty much what I wanted to cover, is very easily on my NVIDIA GPU. Let me also show you the utilization of my GPU when the model is loaded. So let's see. Oh wow, it has pretty much utilized all of my GPU. I should probably close the previous notebook because that was also taking my model. And let's see. Okay, so yeah, so this is reduced. Phew. Okay, so while this is generating the test split, and now it started training the model. So we have a batch size of 4. Has it started training the model? Maybe not, so not right now. Let's see what this does. But in any case, this will train the model, and yeah, it is, because your model size will balloon in GPU when you start training, because now you have to save the optimizer states and everything. So okay, yeah, so because we were only training for very limited number of steps, I think I defined the steps earlier, and it was only 5 steps. That's why we only trained for 5 steps, and then we saved the model. So that's good. And here, because we're only training the adapters, it is not so heavy. So that is basically what I wanted to cover. Now, wrapping things up, I want to quickly describe the dataset. Again, it's not relevant, but still, and what the SFT trainer is doing. So let me switch over to the dataset and the SFT trainer. Okay, so here I have the dataset, the chart dataset, and let's look at a particular type. So you have a prompt that gives you like some kind of instructions, and then user assistant conversations. And the goal is maybe you just want to train on the assistant responses. And it is a multi-turn conversation because you can see user, so each turn is a user question or conversation bit, and then an assistant response. That's one turn. And here we see there are multiple turns, so depending on like what you want to do. So this is sort of a data set, I guess, directly from Hugging Face team. The last thing that I wanted to cover is this SFT trainer. So this one is, I believe, can do both. It can do your standard fine-tuning, next token prediction, but it can also make use of the other thing that I talked about, only teach on the instructions. Yeah, let me see if in, so yeah, here, for example, advanced usage, train on completions only. So which is very important because you don't want to train your model on the instructions or what the user is saying. You want to only train it on the responses. And the way it is done here, basically, this trainer supports collators that let you modify your loss masks. So here, for example, in this question answer format, I only want to train on the answer. I just pick up a response template and I specify that the collator should have that response template. So what that means is loss is only computed over anything that occurs after these answer tokens. So that's why this is quite a useful trainer. I mean, you can do the same thing with Hugging Face trainer, but then you will have to write a bit of manual code. But this just does it out of the box. So I suspect we will end up using this trainer for our fine-tuning needs. So I think that concludes this video. Now we've gone about 20 minutes. Next time we will see the image model, and then after that we will start combining things together. I hope you like this video, and please like and subscribe if you like this kind of content. All right, see you guys next time.